MP3, WAV, FLAC, MP3. How is it possible that there are dozens of file formats to store sound? It's just sound. Well, it turns out it isn't that easy, but it also can't be that difficult. To understand how sound is recorded, let's start in 1967. At that time, the first ever fully digital sound recording took place in Japan. And a few decades later, we can stream high-res lossless audio. What's even more interesting is that the way we capture audio digitally hasn't really changed. Before diving into the digital realm, let's take a look at audio in the real world. Sound is a pressure wave. That means that air is compressed and rarefied over time. When speaking, for example, this is done by your vocal cords and your mouth. The thing is, a computer only understands electricity, so engineers found a clever way to translate pressured air. A microphone converts these pressure variations into a continuous analog voltage signal, so we end up with this voltage versus time curve. Here we run into the first problem. A computer can't deal with the continuity. The reason is quite obvious. A computer can only store a finite amount of data. Somehow we need to turn this continuous curve into discrete numbers. This is sampling. We measure the voltage at regular time intervals. You might have already heard the term sampling rate. The sampling rate describes how many samples are measured per second. For telephone quality, the sampling rate is typically 8 kHz. For wideband speech, it's 16 kHz, and for audio apps, it's more likely 44 to 48 kHz. When sampling, the Nyquist-Shannon sampling theorem plays a big role. It states that to faithfully capture a signal containing frequencies up to Fmax, you must sample at least twice that frequency. Otherwise, you end up with an artifact called aliasing. Human voice is a bit tricky here. The fundamental frequency of our voice is roughly 80 to 300 Hz, but the intelligibility of speech extends to about 8,000 Hz. Telephone systems used to limit speech to 300 to 3,400 Hz, which is why the quality sounds quite thin. So they extended that up to 8,000 Hz to ensure enough headroom above the useful speech band. In modern systems, use even higher frequencies up to 48 kHz. But sampling only handles the time axis, so we also need to discretize the voltage levels. And this process is called quantization. What is done here is that each sample's amplitude is rounded to the nearest value on a fixed scale determined by the so-called bit depth. A 16-bit depth allows for 65,536 possible amplitude levels, which is CD quality. A 24-bit depth allows for about 16.7 million levels, which is used for studio recordings. Due to the rounding, this also introduces an error known as quantization noise. There's a handy rule of thumb here. Bit depth directly determines the signal to noise ratio, so 16-bit gives roughly 96 decibels of dynamic range. Okay, so now we have sampled and quantized our signal. What we end up with is pulse code modulation, the most foundational raw format in audio processing. A PCM file essentially assigns each sample index an integer that represents the voltage. This is what is stored in .wav files. The bitrate here is bitrate times frequency times bit depth times channels. But it would be very impractical to keep the raw PCM because speech has redundancy. Lossless audio compression exploits the statistical redundancy in the waveform and is perfectly reversible while achieving a modest compression of about 50%. An example file format is FLAC. MP3 is an example of lossy compression, where frequency components that humans can't easily hear are discarded, achieving a 5 to 20 times size reduction. To be honest, I always thought that audio recording was real wizard crap, but it turns out it's just clever thinking and very reasonable to understand. There's much more to touch on here, like what role the Fourier Transform plays, but I skipped that deliberately as I just wanted to give you a simple insight in how audio processing works.